Yeah, I would like to welcome all of you to this lecture on the Rayleigh-Benard convection, and what we are going to talk about today is how to do the linearization of the problem around the steady state. In the previous lecture, we had derived the steady state of the natural convection problem. Here the problem we are investigating is that of a liquid film between two plates located at y is equal to 0 and y equals h. The fluid inside was stationary. So, the steady state was characterized by USS, the x component of velocity being 0, VSS, the y component of velocity being 0, and since the liquids were not moving, the mechanism of heat transfer from the lower plate to the top plate was only because of conduction, and that gave you a linear profile for temperature, which is y divided by h times Th T0 and y is equal. So, the temperature of the plate at the bottom is T0 and the temperature of the plate at the top is Th, and that is the linear steady state, and what we had was this as the y direction and this as the x direction, and again it was extending to infinity in the z direction. So, the velocity and the temperature of the steady state are given by this, and corresponding to this you had a pressure at the steady state which was going to be hydrostatic, and that was given by dPSS by dy equals minus rho g, which we wrote as minus rho naught times 1 plus beta times TSS minus T0 times g. So, this is what we saw in the last class. We had derived the steady state equations, and this basically correspond to a liquid which is a fluid which is stationary, and there is a linear temperature profile, and that is the pressure head which is basically hydrostatic. Only thing is, what we have done is we have taken into account the fact that the density is a function of temperature. So, once you know the steady state temperature, you know how the density varies in the quiescent state where the liquid is stationary, and you can just substitute that here and you can calculate what the pressure gradient is. Now, this particular steady state is going to be a steady state for all values of T0. So, this is always a steady state. This is always a steady state. So, what that means is this is always going to satisfy the differential equations and the boundary conditions. What we want to do is ask the question, is this going to be experimentally observable, and like we discussed in the last class, for sufficiently high values of temperature you will realize that the buoyancy forces are going to dominate and convection is going to start kicking in, and the quiescent fluid, the stationary fluid, is no longer going to be able to sustain the heat transfer from the bottom plate to the top plate. and our job is to find out the point at which the convection is going to get initiated. Okay. And what we are saying is that the onset of convection occurs when T0 exceeds a critical temperature, a T0 critical, and when it is more than the critical temperature you will see convection, and our job is to find this T0 critical, and the transition from the stationary state to the state where you have convection is going to be decided by the point at which this particular steady state becomes unstable. Okay. So, T naught at T naught critical, this steady state becomes unstable. So, there is an onset of instability. Here we have an onset of instability. Now, what we want to do is find out this onset of instability. So, in order to do that, we are going to impose perturbations on the steady state, and we are going to look at how these perturbations actually evolve with time. That is the strategy. Okay. And all the variables which are dependent are expanded as u equals uss plus epsilon u tilde, v equals vss plus epsilon v tilde, t is tss plus epsilon t tilde, and pressure is pss plus epsilon p tilde. So, what I am doing here is just trying to tell you that the perturbation, these represent infinitesimal perturbations. The epsilon here has been included to basically tell you that the magnitude of the perturbation is infinitesimal. Okay. What we are going to do is we are just saying that the deviation of the actual u is the actual velocity in the x direction, the deviation of this from the steady state value is the perturbation. Okay. And the magnitude of the perturbation is small, and that is being signified by the parameter epsilon in front of the perturbation. Now, our job is to find out how do these perturbations evolve with space and time, and each and every one of these perturbations is going to be a function of x, y and t. We want to find out how do these perturbations evolve with space and time. And so, what we are going to do is we realize that the u, v and t and p, they satisfy the equation of continuity, the equation of momentum and the energy equation. We are going to substitute for these variables in terms of the steady state and the perturbation, and then get the equations which actually describe how the perturbations are going to grow. In the process, what we are going to do is invoke the fact that we are interested only in small perturbations. We are going to therefore retain terms which are of order epsilon, because this infinitesimal, the terms which are of higher order of order epsilon squared and above are going to be very small, and therefore we are justified in neglecting them. In other words, this is similar to doing a Taylor series expansion of a function around a point where you take only the first derivative term, you do not take the higher order derivative terms, okay. And this Taylor series expansion of a function is valid as long as you are not too far away from the point around which you are doing the Taylor series. So, we are going to substitute these in the governing equations and get the equations which describe the perturbed variables. We begin with the equation of continuity, which is du by dx plus dv by dy equals 0. This is the equation of continuity, and here I am going to substitute for u and v from these expressions here, and this gives me basically d by dx of uss plus epsilon u tilde plus d by dy of vss plus epsilon v tilde equals 0. What we do is we group terms which are of order epsilon to the power 0 and of order epsilon to the power 1, and we get duss by dx plus dvss by dy plus epsilon times du tilde by dx plus dv tilde by dy equal to 0. Now, we want this to be true for all values of the functions in the perturbation, and since this is of order 1 and this is of order epsilon, the only way this equation can hold is if these are individually 0. In other words, this implies by at order epsilon to the power 0, if I look at the terms at order epsilon to the power 0, I have 0 there, I have duss by dx plus dvss by dy equals 0, and at order epsilon to the power 1, I have du tilde by dx plus dv tilde by dy equals 0. Now, whenever you do a linearization around a steady state, the at order epsilon to the power 0, you will recover the steady state equations. At order epsilon to the power 1, you should get a linear equation which is homogeneous, and that is basically what we have here. We have an order a linear equation which is homogeneous, and all I am doing is how did I get this? I got this by writing the coefficients of epsilon. This has to be independently 0 and this has to be independently 0, and that is what gives me this. In this particular problem that we have, USS is 0 and VSS is 0, so this is trivial, but this may not be true for a general problem. In other words, what we have found out is that the perturbed u velocity and the v velocity also satisfy the equation of continuity, and this is going to be something which we are going to use later on, and I am going to write this right here. So, I am just going to use this later on. So, now the next equation that we are going to tackle is the x momentum equation, and in the x direction we have this is the x momentum equation, and what I would do now is I am going to substitute for u in terms of my steady state and my perturbation. I am going to do the same thing for v and I am going to do the same thing for p. Okay. What this results in is d by dt of u naught plus epsilon u tilde plus u naught plus epsilon u tilde times uss x of uss plus epsilon u tilde plus vss plus epsilon v tilde times d by dy of uss plus epsilon u tilde, which equals minus dpss by dx plus epsilon p tilde plus mu times del squared uss plus epsilon u tilde. What we will do now is again equate terms of order epsilon to the power 0 and of terms which are of order epsilon to the power 1. So, at order epsilon to the power 0 we get duss by dt plus uss times duss by dx plus vss times duss by dy equals minus dpss by dx plus mu del squared uss. And this is basically your steady state equation like I mentioned earlier, and our steady state is the trivial steady state where the x velocity component is 0. So, all these terms go off and this goes off and we say that there is no pressure gradient in the x direction. Now, at order epsilon to the power 1, what do we have? This term is going to contribute and we write the equation as du tilde by dt plus, now remember uss is 0. So, epsilon u tilde times this term is going to be 0 and what is going to remain, and this uss is 0 and this uss is 0, and what is going to remain is a term which is of higher order. Okay. This is a term of order epsilon squared. So, we do not need to worry about this term here. Similarly, here we do not need to worry about any term here because vss is 0, uss is 0, and when I multiply these two out I get a term of order epsilon squared. So, these are higher order terms and I do not worry about this. Okay. There is a term of order epsilon squared which I do not worry about. What I am left with is minus dp tilde by dx plus mu times del squared u tilde. Okay. I want to basically explain to you this order of epsilon squared term. Remember that uss is 0 and therefore, what is remaining here is epsilon times u tilde times d by dx of epsilon u tilde is a term of the form epsilon squared du tilde by dx times u tilde. This is a higher order term, this term is of order epsilon squared and that is the term here, and therefore, we do not consider this term. What we are left with is only these terms which are remaining. So, in other words, the linearized equation around the steady state, the x momentum equation is going to be given by this term here, du tilde by dt equals minus dp tilde by dx plus mu del squared u tilde. So, this again is a linear equation, okay, and of course, it has dependency in t and x and y. What I like to do next is look at the y momentum equation, and in the y direction I have rho naught, I believe I am missing a rho 0 here, okay. I missed a rho 0. So, rho naught times dV by dt plus u dV by dx plus v dV by dy equals minus dP by dy plus mu del squared v minus rho g. And what I would like to do is remind you that the y direction is pointing upwards, and therefore, this body term gravity being downwards is associated with a negative sign. And remember, this rho is nothing but I am going to rewrite this rho as minus rho naught times 1 plus beta times T minus T 0 times g. So, that is basically incorporating the density dependency on temperature in the gravitational term, and like I mentioned, this is important because this is the one which is going to give me my buoyancy force, which is going to drive the fluid motion, okay. And this is the Business approximation, because I have retained the density dependency on temperature only in the gravitational term in the y direction and nowhere else, everywhere else I am treating density as being a constant. So, this comes from the Business approximation. So, the rho g term is approximated that way, where we are only assuming a linear dependency of density on temperature. Now, what we have to do is substitute for each of these variables in terms of the steady state variables and the perturbed variables. This gives me rho naught times d by dt of Vss plus epsilon v tilde plus Uss plus epsilon u tilde times d by dx of Vss plus epsilon v tilde, okay, plus Vss plus epsilon v tilde times d by dy of Vss plus epsilon v tilde equals minus d by dy of Pss plus epsilon p tilde minus rho naught times 1 plus beta times Tss plus epsilon t tilde minus T naught g. So, all I have done is taken the y momentum equation, okay. These are equal, okay, because of the Business approximation. All I have done is taken the y momentum equation and I have substituted each of the variables in terms of the steady state and the perturbation variables, and keeping in mind that I have an infinitesimal perturbation, I have put in the factor epsilon in front of the perturbations, okay. Similarly, for T I have Tss plus epsilon T tilde. Now, we look at terms at order epsilon to the power 0. We get rho naught times dVss by dt, that is this term, and you also have Uss multiplying dVss by dx, that is of order epsilon to the power 0. The other terms will contain epsilon, so we do not take that into account, plus I have one term here by dy equals, here on the right hand side I have minus dPss by dy and this gives me minus rho naught times 1 plus beta times TSS minus T naught times G. So, this is the equation at order epsilon to the power 0, okay. And like I mentioned earlier, the equation at order epsilon to the power 0 should give me my steady state equation, and remember at the steady state dVSS by dt is 0. So, all these vanish because we have USS and VSS equal to 0, and what I recover is the fact that I have 0 equals minus dPSS by dy minus rho naught times 1 plus beta times TSS minus T0 times G, and this is the hydrostatic pressure difference in the y direction at the base state, which is stationary, okay. And the density dependence on and TSS, remember, is a function of y, which we are going to determine now. Now, what is this equation at order epsilon to the power 1? I need to take this equation and I am going to erase this on top and take the terms which are of order epsilon to the power 1. Again I have rho naught times dV tilde by dt plus I do not have any term of order epsilon here, because this is u tilde multiplied by dVSS by dx, VSS is 0. So, this does not contribute, and this USS is 0. So, this does not contribute. So, again these terms do not contribute at order epsilon, they only contribute at order epsilon squared, because you can see that USS and VSS are 0, and the only contribution is going to be at order epsilon squared when these two terms multiply, okay. And so, we do not worry about these two terms. What I get is minus dP tilde by dy minus, that is this term here, minus rho naught into beta minus rho naught into beta times T naught. So, because there is a negative times T tilde times G, okay. So, this is the term here of order epsilon. The terms of order epsilon to the power 0 are already taken into account here. This is of order epsilon to the power 0, so is this, that is taken here at the steady state equation. So, this is my linearized equation, okay, around the steady state for my perturbed variable, and this basically again is linear and it is homogeneous, and that is a check for you to make sure that the equation you have derived is actually right. So, I have rho naught into dV tilde by dt equals minus dP tilde by dy minus rho naught beta T tilde G. So, we have one more equation to linearize, and that is the energy equation, and which we will do now. The energy equation is dy equals k del square T, and again I am going to substitute here in terms of the perturbation variables to get rho naught Cp d by dt of TSS plus epsilon T tilde plus USS plus epsilon U tilde times d by dx of TSS plus epsilon T tilde plus VSS plus epsilon V tilde times dt SS by dy plus epsilon t tilde equals k times del square TSS plus epsilon t tilde. So, what I have done is basically substituted for the variables in terms of the steady state and the perturbation, okay. And at order epsilon to the power 0, what do I have? I have dTSS by dt plus USS dTSS by dx on the left hand side plus VSS into dTSS by dy equals k del square TSS. And at steady state the TSS time derivative is 0 and USS is 0. So, this knocks off and all I have is k del square TSS is 0 and I get the linear profile, okay. Now, at order epsilon to the power 1, what I have is rho naught Cp into dt tilde by dt. Now, the steady state temperature is not a function of x, it is a function only of y, and therefore, this does not contribute and I have a higher order term here, okay. This term is going to be of order epsilon squared. I do not have any epsilon order term here because USS is 0 and this is of order epsilon and this is of order epsilon because the time there is steady state temperature does not depend on x. However, here if you look at it, VSS is 0 and V tilde is of order 1, but the TSS is a function of y, the steady state temperature is a function of y, and therefore, I will get an order of epsilon term here and that is going to be given by V tilde times dTSS by dy, okay, and which is equal to k times del square t tilde. So, the point I am trying to make here is very simple. This is my linearized energy equation and that gives me rho naught Cp times dt tilde by dt plus V tilde dTSS by dy equals k times del square t tilde, okay. I just want to explain to you again why this does not contribute to order epsilon to the power 1. This is 0 and TSS does not depend on x. So, the time derivative is 0 and therefore, I only have a higher order contribution. However, here the steady state temperature is a function of y because I do have a linear gradient in the y direction and this when I multiply it with this when I multiply it with this term I will get an order epsilon to the power 1, okay. This is 0 and therefore, this does not contribute to the order epsilon. So, I hope that is clear and what I have is this equation here. So, I have now a system of 4 equations which are coupled and if you recall dTSS by dy is nothing but Th minus T0 divided by capital H because my gradient is linear. The point to note here is that I have 4 equations for my 4 perturbed variables and all of these are coupled to each other. U tilde depends on V, U depends on P, P depends on V and T and this depends on V. So, it is necessary for you to solve all these equations together simultaneously. So, what we would like to do is like to do this systematically and I rather than try to solve for 4 dependent variables, I like to reduce the number of dependent variables, okay. And one way to do that is to eliminate 2 of the variables. It is like having a system of 2 equations and 2 unknowns. You use the first equation and then use the first equation to eliminate one variable from the second equation, and then you get one equation and one unknown. So, we are going to do something similar. I am going to realize that this depends on the partial with respect to x and this depends on the partial with respect to y. I am going to differentiate this equation with respect to y, I am going to differentiate this equation with respect to x, okay, and subtract. So, let me number these equations. So, this is 1, this is 2, this is 3 and this is 4. I am going to differentiate 2 with respect to y, 2 with respect to y and 3 with respect to x and subtract. What do I get? Rho naught times d by dt of du tilde by dx, sorry, du tilde by dy. I am differentiating this with respect to y, equals minus the second derivative with respect to x and y plus mu times second derivative of du by dx, okay. And then I have rho naught times the d by dt of dv tilde by dx equals minus d square p by dx dy plus, did I miss out the viscosity term in the, I believe I have missed out a del square v tilde term here, okay. So, you must go back and write this term here mu del square v tilde and I have mu del square dv, okay. All these are, remember, tilde variables, all these are perturbation variables, okay. Mu del square dv tilde by dy, sorry, I am differentiating with respect to x, minus rho naught beta g d tilde dx. Okay. So, I have missed out this term and you need to make sure you include this in your notes, and when you subtract this I get rho naught times d by dt of du tilde by dy minus dv tilde by dx equals mu times del square of du tilde by dx minus, why am I making these mistakes? This should be y. By dx x. That is what I get. Okay. So, I have eliminated the pressure P from the second and the third equation. I still have this equation now, which is a linear combination of the second and third, but I would like to now eliminate u tilde from this equation, because if I eliminate u tilde then this equation will contain only v tilde and t tilde, and I have the fourth equation which contains only v tilde and t tilde, and I will have two equations and two unknowns. So, now how do I eliminate u tilde from these equations? I need to go back and look at the equation of continuity here. When I look at the equation of continuity here, I realize that I have du tilde by dx in the equation of continuity, and to get du tilde by dx, what I am going to do is I am going to differentiate this equation with respect to x, okay. So, let me recall again what we are trying to do. We are eliminating pressure here by doing the derivative of this with respect to y, this with respect to x, and subtracting. The mixed derivative cancels, and now I have an equation reading u and v and temperature, and to eliminate u tilde I differentiate this with respect to x. If I do that, I get rho naught times d by dt of d square u tilde by dx dy minus d square v tilde by dx squared equals mu times del square of d square u tilde by dx dy minus d square v tilde by dx squared minus rho naught beta g d square t tilde by dx squared. So, I got this last equation by differentiating this equation above it with respect to x. Now, d square u by dx dy is nothing but d square u by dy dx, okay. And remember, from equation of continuity, du tilde by dy, du tilde by dx is the negative of dv tilde by dy, and therefore, this is minus d square v tilde by dy squared from my continuity equation 1. So, wherever I have the mixed derivative of u tilde, I am going to substitute it with the second derivative of v tilde with respect to y, and that basically gives me rho naught multiplied by d by dt of the negative of v tilde with respect to x squared minus d square v tilde by dy squared okay. I should actually write it the other way, and let me write it the right way. It does not matter, but still equals mu times del square of minus d square v by dy squared minus d square v by dx squared minus rho naught beta g d square t tilde by dx squared. I can erase this now. So, what have we done? We have used the equation of continuity to eliminate u tilde, okay, and we did that after differentiating this equation with respect to x, and then we got this equation. This, remember, is nothing but the Laplacian, and this can be written in a compact form as d by dt of minus del square v tilde equals mu times minus del power 4 v tilde. I have some propensity to miss the tilde on these variables. X squared. So, we have this equation here which basically relates the perturbation in V to the perturbation in T. I have eliminated U and pressure, okay, the perturbations in the U and pressure. And if you recall the fourth equation, this also relates the perturbation in temperature to the perturbation in the velocity. And so, what I am left with is rho naught Cp times d by dt of t tilde plus V tilde times T h minus T 0 divided by h equals mu times minus del power 4 V tilde minus, oh that is no, sorry I just got carried away, del square T tilde, okay, I just jumped equations, okay. So now this equation is nothing but the perturbed equation which I had for the temperature, okay. I have done no modifications to that. This relates T tilde, the perturbed temperature, to the perturbed velocity in the y direction V tilde, okay. And I use the equation of continuity and the equations of momentum in the x and y direction to eliminate u and p, and what I got is this higher order equation. I had a second order equation for V tilde. Because of the elimination of u and p, I have got a fourth order equation in V tilde, okay. And the important point is now this equation connects V tilde to T tilde, this equation connects V tilde to T tilde. I had originally a system of 4 equations in 4 unknowns. I have eliminated 2 and I have now a system of 2 equations in 2 unknowns, and hopefully these are going to be easier for me to solve. And what we will do in the next class is actually see how we can go about solving these equations and getting some insight into the calculation of the critical lower plate temperature at which the convection gets started. Thank you.